Alright, so in this section we're going to go over eigenvalues and the characteristic polynomial. So we're going back to eigenvalues and eigenvectors. This section is a pretty no-brainer. Once we find eigenvalues, it's pretty straightforward what this represents and what the characteristic polynomial is going to end up being. Okay? So again, we're going to go back to finding the actual eigenvalue themselves, so basically finding the determinant of the matrix, or this type of matrix. So first off, remember when we talked about finding the determinant, we actually get a lambda, right? So it was kind of like, example, something like this. And we end up solving it, right, just factor it down to get the actual lambda values themselves. Well, if I just change lambda to like x, for instance, now notice we have a polynomial. And that's pretty much what this represents. It's basically saying if we find the determinant of this, we actually get a polynomial. And therefore, when we actually solve for it, right, solve for the actual lambda values, well, what are those? Those are the roots. Those are the actual values that make this 0. That's pretty much what these three definitions are all about. So let A be an n by n matrix, then the determinant of this is a polynomial of degree n, which makes sense, right? If we have a 2 by 2, we have that. So a 3 by 3 gives you power of 3 because we multiply by the diagonal. So that doesn't, that's pretty straightforward. And then the next definition just tells us the actual, the polynomial itself. So p lambda, or sometimes some textbooks use p of t, is that determinant itself. So for example, with my example here, I just change this to t, and that's called the polynomial itself. And therefore, because we have this definition, we have a theorem. Let A be an n by n matrix, so P is the characteristic polynomial for A. Therefore, the roots of this are actually the equivalent to 0. Right? So these are the actual eigenvalues themselves. So it's something we've already talked about. Just now they just get an actual definition and a name for it. So when I'm asked for the characteristic polynomial, it's basically saying that right there, okay? Or the determinant itself. Okay? So because of this, we have a couple consequences of it. If we have an n by n matrix, that means we have at most n distinct eigenvalues, right? Where again makes sense if it's a 3 by 3, we have lambda to cubed, but we can have repeats, right? For example, we can have this, right? It's still technically a degree of 3, but we have 2 repeats. An n by n matrix always has at least one eigenvalue. Again, also kind of makes sense. But it could be, the best part, imaginary numbers. We'll talk about that in a little bit. And then finally, something we've all done is you could break it down to its factors, right? Meaning you could factor this, all the rules of factoring apply to this. Nothing too crazy, basic factoring methods. We're not going to go into discuss rules of signs and all that, breaking down a huge polynomial, but technically, once you get to 4 by 4, it gets a little harder to do so. Okay. So why don't we do a couple practice problems here so you can see how this is going to go about. So first, find the characteristic polynomial and the eigenvalues of each matrix. So nothing's really changed. All it's saying is just find the eigenvalues. So it's just starting with this off, and then finding the determinant of that. So this gives you, let's see. Gives me that. So this is our characteristic polynomial done. So therefore, just solving for x, right, just the x method, you just get 6 and -2 as your eigenvalues for A. Okay. Same thing comes to part B. So breaking this down gives us about that. And this goes actually back to part B. So A was this situation. We have at most n distinct, right? We started with a 2 by 2, so we have two distinct eigenvalues. This one, however, deals with part B, with the imaginary part, because this actually is not factorable. You have to use the quadratic formula for this, and you end up getting with lambda equal plus 2 plus or minus I. So we have our imaginary part here. Okay. And the same thing applies for C. And this one, just give a couple steps to do so. Right, so determinant 3 by 3 is the cofactors of it, if you want to break it down in that format. But basically ends up being this. Oops. So there's our characteristic polynomial, and this one we actually have three distinct roots. There we go. Okay. So like everything else when it comes to processes, we deal with the inverses, we do transposes, now we're doing eigenvalues, eigenvectors. Same thing applies here. We can do different stuff with it, and that's roughly what the next theorem is about. So this one says let A be an n by n matrix, and let a lambda be an eigenvalue of A. Therefore, all of these three must apply. So again, this is saying lambda is an eigenvalue of just A. So therefore, if I raise it to some power, that is an eigenvalue of A raised to that exact same power. Okay. B, if A is non-singular, then 1 over lambda is an eigenvalue of A inverse, which means you don't actually have to solve for all these. You actually, as long as you have this one, you have these three apply. So that's kind of nice. And if A is a scalar, then lambda plus alpha, or A, is an eigenvalue of A plus alpha I. Okay. So kind of obscure ones, but you'll see it's actually kind of nice going forward, because if you want to find the eigenvalues of the inverse, it's actually just have to do it once. You don't have to do it twice. Just find the eigenvalues here and just do 1 over them, and vice versa for the other two. Okay. All right, so we're going to prove the first one, just A. So I'm just going to write my hypothesis. So let A be an n by n matrix with lambda is an eigenvalue of A. Okay, so we want to show this is eigenvalue of this as well. Now, when it comes to a proof, this is a proof of theorem, you can see it anywhere, but in general proof, right? What you really want to do is start, okay, what's that mean? Okay, so knowing that this is an eigenvalue of that, this is saying that AX is equal to lambda x, right? That's the basic definition of what an eigenvalue is. Okay. Well, we also implied, well, that means I'm actually technically solving for this, right? That's what it really represents. Okay. And if I just add this over, really, this is saying that the matrix A is equal to some lambda times the identity matrix. And this is actually what we really care about, is if I could show this, that means everything else applies back to that being an eigenvalue. Okay, so we're going to start here. So we know this is being true. Okay, so now what I'm going to do is I'm going to raise this side to the kth power. Well, if I do one side, I got to do the other side. Okay. Well, lambda is just some scalar, so it's just lambda to the k power times I to the k power. Okay. So I'm going to do a little side note here. We got to figure out what in the world I to the k value represents. Now remember, this is exactly just like exponents, right? This is I times I times I times I times I all the way I, and we have k of them. Okay. So now the question becomes, what is this equal to? Well, the identity matrix times itself times the same identity matrix is still I, the identity matrix. So it doesn't matter how many times I actually multiply by itself, I'm still going to get the same identity matrix. It's kind of the same process like 1 to the 5th power is the same thing as just 1. It doesn't matter what the power is, it's still going to be 1 because it's just 1 times 1 times 1 times 1 times 1. So really, this is all just I itself, which is nice because if I resubstitute this process here, I get that. Okay. Well, again, what does this mean? By just going the same process backwards, that's saying this is true. Well, that's saying that's true. Well, this is the definition of an eigenvalue, so check, it works. Okay. You can actually show this also by induction, if you guys know what an induction proof is and stuff like that, but straightforward algebra is good enough for this one as well. Okay. So now let's actually put it into practice. All right, so we want to find a to the 5th, the eigenvalues of a to the 5th, the inverse of a, and a plus 2i with this a being this matrix here. Okay. So we've already did this one before. It's the same matrix here. So we have those eigenvalues of 2, 1, and negative 1. So I'm just going to write that down. That's the eigenvalues of this matrix A. And we're going to use this theorem. So according to the theorem above, if I want to find the eigenvalues of a to the 5th, all that's saying is I'm raising every single eigenvalue here to the 5th power. That's what this one says, and we just proved it. So I just do 2 to the 5th, which gives you 32. 1 to the 5th, which just gives you 1. And then negative 1 to the 5th, which still gives you negative 1. Check. I mean, didn't have to do any work to get there. So now let's find A inverse. So again, we're not actually finding the inverse, we're actually finding the eigenvalues of A inverse. And this time is using property B. B says it's just 1 over the actual lambdas themselves. So let's do exactly that. So all these are going to be fractions. Well, some of them are fractions. 1 over 2, 1 over 1, which is 1, and 1 over negative 1, which is just negative 1. And then the last one is a plus 2i. Again, going back up here, our alpha in this case will be 2 in this part C part. So all I have to do is just add alpha to each individual lambda, and that guarantees it. So again, alpha is 2 in this case, so every single eigenvalue I'm just going to be multiplying by, or it's not multiplying, by adding by 2. So 2 plus 2 is 4, 1 plus 2 is 3, and then finally negative 1 plus 2 is 1, and we're done. So the last part of this section is actually a very interesting one, and it goes over only a particular type of matrix. It's called a triangular matrix. Well, first off, let A be an n by n matrix. Therefore, A and A transpose have the same eigenvalue, which is, again, kind of nice, especially if you're given one or the other and asked again to find the eigenvalues. You don't have to do all the work for transposing it, do all that fun stuff. It's simply just understanding that it's actually kind of nice. Next one, let A be n by n matrix. Then A is singular if and only if lambda, you have some lambda equaling 0 as an eigenvalue of A, which again is another process to check for singularity. Okay. Now this is actually kind of a nice one because you can actually break stuff down using this theorem. And so let T be a n by n triangular matrix, and a triangular matrix is something like this, where these dots are just random numbers. The ones that I really care about is these individual entries there in the diagonal. And again, why it's called triangle is because you actually get a triangle of zeros. That's kind of the reason why they just call it that. Then the eigenvalues of t are the diagonals entries, and that's the key thing, are the diagonal entries going across. So in other words, the eigenvalues is A, B, C, and D in general here. Again, only if it's in this process here. So, for example, if we do the same thing here, notice we have our diagonal. So my eigenvalues are exactly those four numbers, 1, 4, and 2. There's 2 repeated, it's just 2 itself. Okay. Now, we wanted the characteristic polynomial as well. If I just go backwards, this is the same thing as saying 1 minus lambda, or just subtracting each one individually. 4 minus lambda, 2 minus lambda, and this is squared. So there's our characteristic polynomial.